So good afternoon, dear students. Am I audible? Somebody please respond. Am I audible? Yeah, thank you, Vinita. Yeah, you have messaged me, okay, in the chat group. Thank you. Okay, right. Thank you for the confirmation. So I think it is good to start now. Right. So yesterday we discussed about how a Java program will write data into HDFS file system, Hadoop distributed file system. In today's class, we'll discuss what are the steps that it involves. So this particular diagram talks about the entire operations. There are totally 7 operations. There are 7 steps. So that are there are 7 steps that are need to be carried out in order in the entire process. So let us discuss each one of them one by one. Right. The first one, actually, HDFS client is having Java virtual machine, JVM is having a Java. So whenever you have a HDFS client, so your Hadoop is, if it is installed in any computer, automatically what happens, so the Hadoop computer is built in with your JVM, Java virtual machine. So we call it as Hadoop client. Hadoop client, initially what it will do, it will create distributed file system object. And this created distributed file object will be notified to the name node. In turn, name node will respond. So where exactly the data nodes are there, what are the data nodes are available for storage. So the same information will be sent to FS data output stream. FS, file system data output stream. It is actually a stream object. So we have seen in the yesterday's program, we have created stream object to create stream object to write contents into that particular the file contents into that stream, through which we are going to store the data in various data nodes. And see, this is very important. The anatomy of file write is very important. Anatomy of file write is very important since we have to take care a lot of replication, and of course reading is very simple. You are reading from only one data node, while you are writing the data into Hadoop system. So what happens, the Hadoop system will certainly has to maintain a minimum replication factor of 3. If the replication factor is not 3, is not beyond 3, so obviously what happens, the entire system is not allowed. So name node will not allow. So that is the reason it is very, very important. So it will maintain a pipeline of data nodes, so that each block is stored in a replication of 3. So that is one very important thing that we should consider. So in the steps, we look into the first step. We look at how files are written to HDFS. Although quite detailed, it is instructive to understand the data flow once it clarifies, the entire Hadoop coherent model. And we know very well Hadoop maintains, data in data nodes, and name node will, monitor the entire process. And of course, look at the same thing we are having. So the case we are going to consider in the case of creating a new file, so writing the file and then closing the file. So these are the three major steps. So creating a file, writing the contents into the file, and closing the file. So whenever you are writing the contents, you should write based on the replication factor, and that too in different data nodes. That is very important point that you need to be observed here. So the client, creates the first step. Client creates the distributed file system, the file, using a create method. So using a create method, it creates. That is the first step. Second, so distributed file system makes a RPC call, remote procedure call, to name node and create a file. Create a file in the file's namespace. So that is, a name node will hold the namespace of all the files. So first, it will create entry in the namespace of the name node, and with number of blocks associated with it. So it will tell. So whenever you are creating a file, so probably you will come to know how much data based on your number of data. So what happens? The number of blocks are being allocated, and based on the same information, what happens? Uh, the replication factor is also notified. Okay, right. The third step, the name node performs various check to make sure that file does not already exist, and the client has the right permission to create the file. If the check passes, the name node makes a record of a new file. Otherwise, the file creation fails. And remember, very importantly, if the file is already existing, so you cannot overwrite the file in HDFS. You cannot overwrite the file, so you can only create the file. That's all. So if the file creation fails, what happens? It will throw an IO error. So that we have seen. So in the program also we have written. So IO error will happen if the file creation is failed. So when file creation will fail, whenever you are having the file which is already existing, so in that case it will fail. So the distributed file system returns a uh, uh, FS data output stream. So this is data output stream. It is written to your distributed file for the client to start writing the data. So output stream is written, okay, and it is ready. So using this output stream only, so the data has to be written into the data nodes, just as in the read case. So FS data output stream wraps the DFS output stream. Okay, so it makes use of DFS, distributed file system output stream, so which handles the communication with the data nodes and name nodes. So this is the node. Certainly, it will take care. It will take care of the communication between your data node and your name node. And of course, that's about step 2. As the client writes the data in the step 3, uh, the DFS output stream splits into packets, which it writes to an internal queue called a data queue. So what happens? Of course, data nodes are stored in, they are different computers. And of course, if you want to store data to different computers, definitely you have to make use of computer network, and your entire data is split into packets, and these packets are being pushed into data queue. And once this data queue is you know is composed, so what happens, the data streamer, okay, the data queue is consumed by the data streamer, whose responsibility is to ask the data node to allocate new blocks by picking the list of suitable data nodes to store the replication. So it will certainly store, get the data nodes details, and based on these data nodes details, what happens, the replicas where it has to be stored, everything, the name node will supply, and data streamer is going to communicate with the name node, and you will get all the details. Once all those details are available, what happens, the list of data nodes form a pipeline in the sense. So the first block is written, next block is written into the next data node, next block is written into the next data node. It's just like, it's a pipe. So for each block, okay, there is a data node, and for the next block there is a next data node, for next block there is the next data node. So it creates a pipeline. So we will assume that replication level is 3. So default replication level is 3. So there are 3 nodes in the pipeline, and of course, certainly these data nodes, actually in the pipeline, you will have the IP addresses of these data nodes. So maybe one IP address is different, another IP address is different, another IP address is different. So the data is stored at different places, and these different racks, different geographical locations based on the IP addresses. So your data streamer will get 3 IP addresses. These 3 IP addresses are nothing but these are the IP addresses of various data nodes. So based on the data streamer IP addresses, what happens? The data blocks are stored. The data streamer streams the packets to the first data node in the pipeline, which stores the packet and forwards it to the second data node in the pipeline. Similarly, the second data node stores the packet and forwards it to the third, that is last. And this is how actually happens. So this is how the data actually stored. It's actually data stored, and each block is stored in 3 different places. And this data streamer will get for every block of data, it gets 3 data nodes IP address. So because the replication factor has to be 3, so that's why for every block it will be done the same way. Okay, so it connects to the name node and gets the 3 IP addresses. These 3 IP addresses are data nodes IP address, and it will be stored. It will be stored in 3 different systems. The next step is the 5th step. Once data successfully stores, okay, the DFS out stream also maintains an internal queue of packets that are waiting to be acknowledged by the data node. Of course, you get an acknowledgement from the data nodes. So that is successfully data, it is stored. Okay, this which we call it as acknowledgement queue. A packet is removed from the acknowledgement queue only when it has been acknowledged by all data nodes in the pipeline. Yes. So once you get acknowledgement from all these 5 data nodes, what happens? So certainly what happens, the data nodes are removed from the queue, and new queue is created for next set of next set of blocks. Next block, new set of data nodes are created. For the next block, again new set. For the next block, again it is new set. So it is just like that. And this is how exactly things happen. What if the data node fails? So out of the pipeline, you get 3 data nodes address. Okay, fine. So you are trying to write first data node, or you're trying to write the second data node. Suddenly what happens? Some data node fails. If the data node fails while the data being written into it, so then the following action has to be done, and it should be transparent to the client while writing the data. So what is the first step? First, the pipe is closed. Immediately, if the data, some data node is failed, automatically what happens? Pipe is closed and new pipe is restarted. Any packet in the acknowledgement queue are added in the front of the data queue. So the data nodes that are downstream from the failed node will not miss any packets. So automatically what happens? So it will be removed. Secondly, the current block in the good data node is given a new identity, which is communicated to the name node. And so the partial block which is failed in the data node will be deleted if the failed data node recovers for later. Okay, so the information regarding the successful data node storage will be there with the acknowledgement. If the acknowledgement is not coming from the data node, so it is deleted. And what happens? The failed data node is removed from the pipeline, and the reminder of the blocks data will be written to 2 good data nodes. Suppose first one is written, second one is having some issue, so it is removed. Second one is removed, and of course second one is having some difficulty. So what happens? The good data nodes are again brought back. The list name list is brought back, and of course it is written. It is pipeline is created. New pipeline is created, and it starts writing. So the name node notices that the block is under replicated, and it arranges for further replication. It is created on another node. So according to replication factor 3, so in the pipeline there should be 3. Since one node is failed, so it will understand and it will arrange for another data node. So another data node that will be added into the queue. Subsequent blocks are then treated as normal. It is possible, but unlikely, the multiple data nodes fail while block is being written. And of course, as long as the data file dfs.replication.min replicas are written, so what happens? Write will not succeed. Okay, so unless you have 3 replication factor, all 3 copies are written, so you don't call the file writing, or the data block writing is not complete. And like this, all the blocks has to write. Even if in the file, if there are 5 blocks, even if some block is having problem, until that entire file block is completely written with the satisfied replication factor, so it is not considered as it is not considered as the complete success. And blocks will be asynchronously replicated across the cluster until its target replication factor is reached. So target replication factor is always 3. So this is what we have to understand, the entire anatomy of your data writing, file writing into the HDFS system. So when the client finishes writing the entire data, so all the blocks, so along with replication factor, it calls the close on the stream. This action flushes all the remaining packets to the data node pipeline and waits for acknowledgement before contacting the success information to the data name node. So it will wait. Once it gets the acknowledgement, what happens? So the name node will send a signal, that is step number 7, signal complete. So with that, what happens? You will certainly, get the information that entire, file and the blocks that are there in the file are written correctly. So the name node already knows which block the file is made up of. So it only has to wait for blocks to minimally replicate it before maintaining the success. So this is how it has to be maintained. So for every block, so the replication has to be maintained and written successfully into data node. And apart from this, your data node also should send a successful acknowledgement so that the entire process is complete. So once the complete signal is sent to the name node, so name node closes the entire connection. This is how the overall file writing is going to be done. Is going to be done in the entire HDFS. So that's all for today's class. In the next class, we'll discuss about Hadoop replacement, and the entire class video is recorded in this